length, just like that. Anyway, if you've had physics, you'd recognize these formulas. So, and if not, it's cool. But if we look at the acceleration then, for this, we differentiate twice, we get two terms. We get minus r omega squared, this vector, and then r alpha, that vector. This is the normal vector, and that's the tangential vector. So as you can see, the magnitude of the centripetal acceleration is r omega squared. Now omega, if you rewrite it in terms of speed, is v over r. So this is straight up v squared over r. That's the centripetal acceleration. The minus is there because it's center seeking. And then over here, r alpha is the tangential acceleration, which makes sense because if you do angular acceleration times alpha, that gives you the rate of change in the speed of the path. If the angular acceleration is 0, the speed's not changing. It's just constant speed, circular motion. All right, anyway, so there's, I know. Listen, if you haven't had physics or you don't care about connecting to physics, this section will not excite you. But I am actually interested in showing you where the formulas in physics come from and like how that all fits together with what we're doing. That is one of my major goals in this course, is like connecting to physics. Although I don't test on physics because, of course, I would like for people to pass this class, right? Physics is enough trouble in the physics course. Let's leave it there, all right? But I hope you can tolerate me talking about it. Anyway, here's a picture again. Come on. The acceleration vector, there's a tangential piece and there's a normal piece. And that's all you need. There's never a binormal piece to the acceleration. Oh, the double scrolling has got me again. This calculation, I didn't think was going to work out when I first tried it. So what I'm doing in this example is I'm calculating the arc length of this motion. By the way, when I did that the other day, the marker actually like lined up with the thing. That was not intentional. I'm so happy about that. I need to go back and make that a thumbnail. I never do this kind of thing, but like the thumbnails are whatever. It's whatever YouTube generates. I don't care. You know, that's my post-processing upload. That's the extent of it. Okay, so here I'm calculating the arc length of a parabola. So how do you do that? Well, there's the position, x naught plus v naught xt plus y naught plus v naught yt minus 1/2 gt squared. Here, all of the letters are constants, right? Again, if you've had physics, you'll recognize this. These are the usual kinematic formulas. I mean, usually they give you at an angle, so v naught x is like v naught cosine theta, and v naught y is like v naught sine theta, right? And you figure out how far the ball goes, all that junk, right? These are the formulas. So my question was, what's the arc length of this? I'm like, all right, well, let's try to calculate it. So the velocity is that, which makes the speed the square root of this, right? And then I'm like, well, I was expecting to get stuck on the integration, but it turns out you can do the integral if you know about the hyperbolic substitution. So I made a hyperbolic substitution. I did the integral. After some suffering, after some, calculus 2, which you've by now forgotten, blah, 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 there's a formula for the arc length of the marker that I just threw in terms of the initial velocities and so forth. That's how far, if I could tell you, the initial x and y velocities, I could tell you how far that length would be. Anyway, oh, and this formula simplifies to just this if you make the x velocity 0, right? Because then it's just this, right? Which is easier. I don't think we need calculus to calculate that length, right? You tell me the top multiplied by 2. So distance traveled is arc length. We can go in a circle, right? We can go in a circle back to where we started, right? We did travel a distance, and yet our displacement is 0, right? So distance traveled is arc length. All right. Here's another example. So just to show you some simple examples, here's a curve, t squared plus 1, t cubed, t squared minus 1. Find the velocity, acceleration, and speed relative to the given position. So velocity, differentiate once. Acceleration, differentiate twice. Speed, magnitude of the velocity. Simple as that, right? So if I was to put this question on a quiz, I would allocate like all of 1 minute for it. That's how long this should take you, 1 minute, right? Now, if I ask you to find the, and if I ask you to find the tangent, okay, 1 minute, 10 seconds. The unit tangent, what is it? You just take this, take this vector and divide by what? That, right? If we say 1 over this, 1 over the square root of 8 squared, 8t squared plus 9t to the 4th, times that vector, 2t, 3t squared, 2t, that would be the unit vector. The unit tangent vector is simply the velocity divided by the speed. That's the normalized velocity vector. Okay, fine, another 15 seconds to find that. If to the quiz I add the instructions, find the normal vector, then I owe you like at least another 2 minutes. Like, it's just much worse. Because to find the normal vector, I would have to differentiate the tangent vector, right? Which means I'd have to do what? I'd have to differentiate 1 over the square root of 8t squared plus 9t to the 4th times the, what was it? I got my what? 2t, 3t squared, 2t. And of course, you can do that, right? This would be dt dt. Nothing's stopping you from doing it, but it's going to take you some time, right? But if you could do that, then you can calculate the curvature of the curve, right? Because the curvature is given by the magnitude of this, I think divided by the speed, was it? So, all right. Maybe I have something like that in the next one here. I have a velocity function for Dwight. I think I was watching The Office when I wrote these notes. But so if that's the velocity, and I tell you the initial position of Dwight's at the origin, I say find the position. So to find position from velocity, we integrate, right? So the integral of dr du is equal to the integral of v here. Now the net change theorem for vector for paths gives us that this is r of t minus r of 0. And then we can just integrate that. We get that. And so, voila, there you go. A problem I like to ask on a test a lot of times is, here is the velocity function. Here is an initial position. Then you guys find for me the position as a function of time and the acceleration as a function of time. I like this problem because it gets me, it allows me to see whether you can integrate and whether you can differentiate, and it's just a nice problem to test a lot of the motion stuff all at once. Here's another one. Oh, this one here, I have what's going on here. I've given us initial I've given us acceleration as a function of time, right? And I've given us acceleration as a function of time. Here it is. I told us the initial velocity and the initial position. Now I'm asked to find the velocity and position. So what I do here is I integrate acceleration once, and that gives me velocity. So the velocity is the velocity initially plus this integral, which works out to that. And then I integrate again, right? Integrate again to get the position. So there's two ways to do this. The one way is to integrate like an indefinite integral and add a constant vector, then plug in the initial data to find the constant vector. You can do that. That's one way. The way I'm doing it here is I'm using the net change theorem. So I'm doing a definite integral of both sides. See this integral from 0 to t of like db du is b of t minus b of 0. So I'm using that theorem on the fact that a is dv dt. I'm integrating both sides here, and that's giving me like v of, sorry, lost my place. Oh, goodness gracious. V of t over here minus v of 0, and then I just moved it to the other side, so it gives me v of t is equal to v of 0 plus this integral. Anyway, there's that. Another physics example. Here I'm deriving the usual kinematics formulas. If you like it, wonderful. If you don't, whatever. Now here's one that's actually like the homework problem you asked me about, problem 30. This problem is pretty much problem 30 in your homework, right? So here I have a position. I made it nice. This is a planar curve, right? It's in the xy plane. You can just see it. The velocity is this. And as such, the speed, I'm sorry, that's the velocity vector. The magnitude of the velocity is actually 1 over 1 plus t squared, so I divide by that to get the unit tangent. I differentiate, all right, and simplify to obtain the derivative of the tangent. And if I normalize that, that gives me the normal vector. So I've calculated the tangent, calculate the normal, and then the acceleration. Of course, I can calculate the second derivative. Here it is, right? Then to find the tangential part of the acceleration, I take the dot product with the unit tangent. And to take the normal component of the acceleration, I take the dot product with the normal vector. Listen, there is a workaround here. If you're just after the components, so like the acceleration is equal to a sub t plus a sub n, right? What does that say about the magnitude of a? I want to point something out here. If you're just interested in finding the components, what I'm trying to say is there is actually a way to calculate the normal component to the acceleration without actually finding the normal vector, I believe. Because, so anytime you have a pair of, like t and n are perpendicular, the length of the sum of two perpendicular vectors, you can prove, this is actually a good problem. Work it out. It's the length of this squared plus that squared. So you see, if you can calculate the acceleration, the acceleration's easy to calculate, right? That's just the second derivative. Yay, we're done, right? So that's easy to calculate. The tangential part of the acceleration is relatively easy to calculate because you just take the acceleration and dot with the unit tangent, which is simple enough to find. So since you know this and you know that, you can find the normal component to the acceleration. The magnitude of it, right? So, of course, also kind of dumb, but the acceleration is equal to what? At t plus ann, right? So ann is equal to a minus att. So if you're just after the vector component, if you're after the normal vector component of the acceleration, you don't actually need to find the normal vector, because you know that whatever's not tangent in the acceleration must be the normal piece. See, there's a way to decompose the acceleration into the tangent and the normal without actually calculating the normal.
I know in problem 30 we're supposed to verify that the sums add up.
But 30 has the evil instructions of verify, so you need to actually find the normal. Yeah, sorry about that. But there's a deeper issue, right? Let's see here. All right, so that brings us to Kepler's laws of planetary motion. Who is interested in proving Kepler's laws? Somebody? I may do that, but first I'm going to skip ahead and do the integral along a curve, because that's the last topic before the test, so hopefully tomorrow. Anyway, thanks guys. Sorry if you already knew parametrizations and stuff, but I thought we should just take a step back and spend some time.